Good afternoon, this is Win speaking, and my co-author is Dr. Thanaporn Penrat. Today we'll be presenting atmospheric mercury from coal combustion in Thailand and its implications to ecosystems. The motivation for this study stems from the argument to phase out mercury emissions for reasons which are obvious and can be referred to in the Minamata Convention on Mercury. However, when we talk about coal combustion sources in the context of curbing mercury, the question arises as to what are their contribution to environmental mercury. So to answer this question, we use a three-dimensional chemical transport model, GeoSchem. The model tracks mercury in three species, that is elemental mercury or Hg0, reactive gaseous mercury or Hg2, and particle-bound mercury or Hgp. We first improved the mercury coal combustion emission inventory in Thailand. Then we simulate mercury in two scenarios, the full emission scenarios and another scenario without the coal combustion sources in Thailand. The difference of the two scenarios is the mercury from coal combustion in Thailand or MCCT. Then we look at the linkage to ecosystem impact via deposition of mercury by collecting fish samples for mercury analysis in areas affected by mercury deposition. As mentioned, the first step is improving the coal combustion emission inventory for mercury in Thailand. We used a bottom-up approach utilizing plant-specific data. Ultimately, the crucial information produced in this step is how much mercury gets released and the speciation of the released mercury. We want to highlight the core benefits of conventional air pollution control devices such as PM control, DNOx, and desulfurization units, and that each of these affect each species of mercury in different ways. We use reviewed data for mercury speciation to apply for the emission calculation of each coal plant. The result in this step is an improved emission data in terms of location of release and also an update on the speciation. The proportion of elemental mercury is significantly higher compared to that in the original inventory in GeoSchem. The accuracy of spatial information would mean that we have a more accurate prediction than before, while more elemental mercury would mean that more mercury gets to travel long distance before being deposited or chemically converted to a more reactive form. Now let's look at the model. The result of the MCCT simulation can be summarized in a global budget chart. The numbers on arrows are rate in a unit of ton per year. The numbers in boxes are burden or amount of mercury in the air, shown in the unit of ton. In terms of the sources, apart from the direct emissions, there is a small re-emission of MCCT from the ground after it deposited. Oxidation of elemental mercury produce reactive gaseous mercury on a comparable scale to the direct emission, meaning that these secondary sources can occur far from Thailand. Removal of atmospheric mercury is by deposition, including dry and wet deposition. Deposition is in fact just a transfer of mercury in the air to be mercury in the ground or in water resources. We can look closer at these deposition rates and differentiate between that occurring within Thailand versus those occurring outside of Thailand, labeled as world on these pie charts. Overall, we can see that 80% of MCCT gets deposited outside of Thailand. This emphasizes the transboundary nature of mercury pollution. Now we want to move our focus towards the linkage to ecosystem impacts. So we look at what is occurring domestically. We look at total deposition of MCCT in this map. The loading by deposition occurs mainly in two areas. Let us call them area of deposition influence or ADI. These ADI collocate with the emission sources. So let's look at the deposition rate per area to consider the impact of certain locations. This is a statistical summary of the deposition rates from different model grid boxes in the different areas. The chart highlights the intense local impact of MCCT deposition at ADI1 and somewhat lower at ADI2, while the rest of the Thailand gets much lower MCCT deposition. So we want to link this information towards our fish sampling activities in order to study the implications to ecosystems. We are aware of the fact that the mercury can be observed in the environmental samples would be from all sources, not just coal-fired power plants in Thailand. So we look at the deposition of mercury in full emission scenario along with the contribution of coal-fired power plants in Thailand. The map on the left shows percent contribution of MCCT to the total deposition loading. We set 5 sampling stations to cover both high and low total mercury deposition as well as MCCT deposition. So the major fish species in the 5 sampling locations is Hampala macrolepidota. It is a carnivore at tropic level of tertiary consumer or level 3. The data of the sampled fish and the mercury concentration in fish meat is summarized in the table shown here, along with the statistics presented as a box plot, with the dashed line being the average. We can see that at station A and F, the distribution of mercury concentration is rather broad, and this correlates with the locations with high MCCT deposition. When considering the level of unhealthy mercury in fish meat, WHO recommended that fish with more than 0.3 mg of mercury per kilogram of fish meat, the harm to the brain and IQ outweighs the benefit from the nutrition consumed. We found that at station A, the probability of a caught fish to have unhealthy level of mercury is 40%, which is quite high, and 60% at station F, and 0 elsewhere. So to look at what factors influence the mercury level in fish meat, we did a multiple regression analysis with several factors including total deposition rate, wet, dry deposition rates, as well as deposition rates of MCCT. We found a good correlation between MCCT wet deposition and the mercury concentration in fish meat. Especially if we look at the average concentrations alone, there is a strong nonlinear correlation shown here on the right graph. This shows that MCCT wet deposition contributes majorly to the mercury in fish meat. The result reflects the importance of emitted mercury from Thai power plants that affects the chance of accumulation of mercury in local reservoir and the fish that might be consumed by the local people. So in summary, we want to highlight that GeoSchem model suggests that 80% of MCCT deposition occurs outside of Thailand. While domestically, we found intense MCCT deposition near the emission sources. As for the impact to ecosystems, at reservoirs with high MCCT deposition rates, they have probability of unhealthy level of mercury in fish meat, and mercury levels in fish correlates well with the MCCT wet deposition rates. So this suggests that improvement in the Thai emission data helps with local prediction, while uncertainty in the long-range transport of mercury is still a challenge to the model. Thank you for your attention.